O próximo convidado, temos convidados internacionais, não está lá fora, mas está aqui conosco. O tema da sua intervenção é We Calculate Wrong, a Holistic Ecological Assessment of Transportation Systems. Chamo agora ao palco o Dr. Klaus Radermacher, CEO da KPRBE. Bem-vindo, welcome. I guess in German we say willkommen. Yeah?
Thank you, Marta, for this very nice introduction. She apparently speaks much better German than I speak Portuguese. I'm sorry, but I thank you very much for inviting me anyway. I know I'm the last speaker between you and your well-deserved coffee break, but I'll make it quick, and I hope that you will not regret being here. Anyway, we calculate wrong. That's my main statement. We calculate wrong because if we don't assess mobility systems holistically, as I say, we're not getting the right impression. Why is that? There are 4 mobility systems, no more than that. That is railway, road, aviation, and shipping. It's all over the world, everywhere. And when we talk about the ecological footprint, in particular carbon dioxide, CO2, we almost always only look at the drive energy for the vehicle, what comes out of the tailpipe. And this is why everybody says taking the train is eco-friendly and flying is bad. But that is not true if you look at the systems completely, because what you see here on this matrix is that each and every of the mobility systems requires its own infrastructure. It requires a vehicle, it requires drive energy, that's what we're looking at all over, but then we require a node infrastructure, we require a path infrastructure, and we require a control infrastructure. And all of these infrastructure components are completely incompatible. They're very specific to the very specific system. And that is not taken into account when we assess that and when we speak about carbon footprint. One of the things I'd like to point out on this chart is, if you look at the path infrastructure for aviation, it is air. The air does never have to be built, and it does not to be maintained. There is no maintenance required. That's completely different from roads and completely different from railroad tracks. Same is true for international shipping. If we look at infrastructure, we see there are tons, massive tons of steel, concrete, copper, aluminum that are required for path and node infrastructure. No matter whether you look at airports or train stations, no matter whether you look at streets, at highways, or at railroad tracks. And if we look at the carbon footprint of the materials that are required to build this infrastructure, and I'm not going to read this to you, you can read it yourself. All I'm going to say, there are huge amounts of carbon dioxide that already are being emitted by just getting the materials that are required for the infrastructure. So the CO2 emissions that do not come from drive energy are far too large to be ignored. Few examples. Everyone says taking the train is eco-friendly. But if you look at that, building 1 kilometer of double-track high-speed railroad, that requires just for the track, the steel in the track, the slab track, and so on, depending on what construction method you use, between 800 tons and almost 1,600 tons of CO2 per kilometer. But that's only the track. The moment you have to cross a river, you need to build a bridge, which usually today is built of ferroconcrete. So that's like armed concrete or reinforced concrete. There's concrete with a lot of steel in it. These are the numbers for 1 kilometer of railroad bridge. And it gets even worse with tunnels, because tunnels are built of a concrete shell with a lot of steel in it. So we're getting immense numbers. And then we have the electrification, just that stupid copper wire to get the electricity to the train engine. Copper is quite heavy. 1 kilometer of copper wire just to get electricity to the train is more than 1 ton of copper. more than 1,000 kilograms. I didn't make up these numbers. You don't have to believe me. That's what I always say. All this you can calculate yourself. I did the math, and you can do it the same way. So this is what we're looking at. Now I'll give you one example. A fantastic piece of engineering is the Gotthard Base Tunnel in Switzerland. It's the longest railroad tunnel in the world, 50 plus kilometers in length. 3 tunnel tubes had to be built for that, 1 in each direction and an emergency one in the middle just for emergency cases. So they had to build 152 kilometers of tunnel tube just for a 50 plus kilometer piece of track underneath the Gotthard mountain. And the fantastic this is, but did you know that the tunnel was closed for more than a year because they had an accident in one of the tunnel tubes? So no traffic was going through. Yeah. But what I want to ask you is, do you have an idea of how much steel is built inside the Gotthard Base Tunnel? And we want to compare it with the Eiffel Tower. All of you know the Eiffel Tower. One Eiffel Tower is about 10,100 tons of steel. Now, believe me, in the Gotthard Tunnel structure, there is enough steel to build 21 Eiffel Towers. And it's not only that. If we look at the amount of concrete, this is the 3rd largest pyramid in the world. It's the Pyramid of the Sun, Teotihuacan in Mexico. I like this example because it's almost exactly 1 million cubic meters in volume. 1 million cubic meters. And the amount of concrete that went into the Gotthard Base Tunnel would fill 4.1 or 4.2 of these huge pyramids. And if we look at the excavated material, I mean, if you dig a tunnel through a mountain, there's a lot of soil, there's a lot of rock that needs to be taken out. If you look at that, how much do you think would that be in terms of pyramids of the sun, Pirámide del Sol in Mexico? Well, I answer to you, it's about 28 million cubic meters of excavation material that had to be extracted from the mountain in order to build that railroad track. And this is not done with a sand shovel from the beach. And this is what is almost everywhere forgotten or not discussed when we talk about carbon dioxide emissions from traffic systems. And now there is another aspect when we have to look at mobility. Every form of mobility, no matter whether I walk, whether I take my bike, whether I drive my car, whether I fly in an aircraft, all mobility is applied physics. And there are certain rules, and I'm not going to make this a physics class, don't worry. For those of you who would like to do the calculations at home, they're here on the slides. What I'd like you to understand is, no matter what you do, you need energy for acceleration. You need energy to overcome the air drag. You need energy to overcome gravity. That's what physicists call lifting power, lifting work. And the formulas are here. And the important thing is when you really move a little faster, the air drag supersedes all the other frictional resistances that are there. In a car, you still have friction with your wheels on the street. Also, railroad or trains have friction with their steel wheels on the. We can ignore that as long as we're moving faster than 80 kilometers per hour. The important thing is, and that is what many people do not understand, lifting work is not only required for aircraft. I've very often given presentations that say, yeah, but lifting work only for aircraft because people see how an aircraft takes off from the ground. But that's not true. Whenever you go uphill with your car or whenever a train goes uphill, you also have to perform lifting work. Very same formula. Now, the important aspects in the end are, what is the overall mass to be moved? Because that's important for the acceleration, for the lifting work. What is the number of acceleration processes that you have if you want to go from A to B, like from Frankfurt to Lisbon or from Munich to Lisbon? I just flew in from Munich to Lisbon this afternoon. What is the overall speed you're traveling with? Important for the acceleration energy required and for the energy required for air drag. And what is the overall elevation to be overcome? Bottom line, the more uniform the movement, the fewer accelerations and decelerations, the more efficient is the process of movement. Traffic must flow. It's something that many politicians have not understood because they very often try to do exactly the opposite when we take our cars in the cities. But that, from a physics perspective, the fewer stops you have, the fewer accelerations you have, the better is the energy efficiency of the movement. Now, if we compare train versus aircraft, and these are examples which I've calculated for Germany or Central Europe, a little bit of Switzerland included. If you go from Hamburg to Zurich or from Hamburg to Munich or from Munich to Berlin, if you go by train, you have like 8, 9 or 14 stops in between. That means 14 times the train accelerates to like 270 or 290 kilometers per hour, and the next station it stops to 0, and then that happens again. And it happens again and again and again. And the air drag has to be calculated for each kilometer that you go. Now look at the distance difference between train and aircraft. This altogether means that the movement efficiency of trains, because trains are extremely heavy. An empty ICE train in Germany is more than 400 tons. And with the average utilization, that means that 1.7 tons or 1,700 kilograms are moved and accelerated 7 or 8 times for each single passenger on a trip from Hamburg to Munich. 1,700 kilograms of train plus 100 kilograms of payload. We always deal with 100 kilograms of payload for the passenger, no matter whether it's in an aircraft or in a car. And also cars are very heavy. And when cars are being moved in Central Europe, there's only about 1.5 people in them on average. So they have a utilization of 30% if you have 5 seats. Trains have 56, 57%. Aircraft, even before the pandemic, had 87 or 84%. So you have to take these things into account in order to come up with real numbers, how efficient is mobility and what is the energy that is required. These are the energy calculations I did based on the formulas that I had on the slide before. And that is really surprising. You see that the lifting work, because the train has to go up and down, not 10,000 meters like an aircraft. It's much less. It's only about, what do you have here, 1,894 meters on its way from Hamburg to Munich. It goes up and down a little bit only. But because for every passenger we have a mass of 1.8 tons, 1,700 kilograms from the train plus 100 gram payload, the overall energy required in kilojoules is higher than if you do that with a plane where you only move less than 500 kilograms per passenger. So there is really a lot of much more thinking is required in order to understand the efficiency between train and plane travel. Mobility solutions of the future, that is what I want to talk about, and that is what I want people to understand. You have to think holistically. You have to think holistically when assessing carbon dioxide and other environmental aspects. Calculate, don't guess. It's not a matter of gut feeling. I think, I feel, that's what I always hear. No, doesn't work. Sorry. Never forget the necessary infrastructure. Even if the infrastructure has been built 10 years ago, there are millions of tons of carbon dioxide. They still need to be attributed to the travel performance of today. Utilize the existing infrastructure. I always say that, yes, it doesn't make sense at all not to use a road or not to use a train track that has already been built. We will not get a single gram of carbon dioxide back into an imaginary bottle by not using a train infrastructure or a road infrastructure. But check very carefully, and this is what politicians don't do these days. check very carefully whether more infrastructure is really required in the long term, or can we do better with what we already have. Science and engineering aspects, they must be key for future mobility solutions. Ideology and emotions are not helpful. Can I repeat that? Ideology and emotions are not helpful. Economic criteria must be considered just as holistically as ecological criteria. How much does it cost in the different systems to offer 1 passenger kilometer of transportation? In a train, in a plane, in a car? And then the question is, who pays for what part of it? What fraction is actually part by the person who benefits from the performance, from the traffic performance, and what paid is by the government, or let's say by the general public, us taxpayers? And very important, scientific and economic laws do not care whether they are understood or not. They always apply everywhere, everywhere on this planet, even to those who do not understand them. This is the message in the 15 minutes that I'd like to give to you. I thank you very much for your attention. If you're interested in that, I'll be around for a couple more minutes. I'll be around tomorrow morning, then I'll fly back home. I have a LinkedIn newsletter. I have written a couple of surveys. I've written reports. All of that can be found on the web. And I appreciate for you having listened to me, and now we have all deserved the coffee break. Thank you very much.